Hubble pointed its camera at the edge of the observable universe and found galaxies that shouldn't exist yet. Hundreds of billions of stars. Fully formed spiral arms. Supermassive black holes sitting at their centers. The kind of galaxy that should take billions of years to build. Except these galaxies existed when the universe was only 3 to 500 million years old, roughly 4% of its current age. It's like walking into a maternity ward and finding a fully grown adult standing in one of the incubators. So either our timeline for how galaxies form is wrong, or something happened in the early universe that we don't yet understand. Both possibilities are a big deal, and over the next 50 minutes we're going to go through exactly what was found, why it breaks the leading model of cosmology, what scientists are proposing to explain it, and where this entire debate is likely headed next. Let's start with something simple, what it actually means to look at the edge of the observable universe. Light travels fast, but it isn't instant. It moves at about 300,000 kilometers per second, and that speed limit means that everything we see is old news. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long its light takes to reach Earth. When you look at the nearest star beyond our solar system, Alpha Centauri, you're seeing light that left it over 4 years ago. The Andromeda Galaxy, our closest large neighbor, appears to us as it looked 2.5 million years ago. The further away something is, the further back in time we're looking. And there's a hard limit to how far back we can see, because the universe itself is only around 13.8 billion years old. Light from anything further than that simply hasn't had time to reach us yet. That boundary is called the observable universe, and at its very edge, we're not looking at some distant place in the present day, we're looking directly into the infancy of the cosmos. We're watching the first galaxies form, and the first stars ignite. That's exactly where Hubble pointed its camera, and that's where things stopped making sense. It's worth pausing on just how strange this idea is, because it's easy to say, and much harder to really absorb. Every photograph of deep space is also a photograph of deep time. When astronomers build a map of galaxies at different distances, they're not just building a map of space, they're building a timeline of the universe's entire life story, layer by layer, like tree rings. The nearby galaxies show us the universe as a mature adult. The distant, faint smudges of light near the edge of what we can detect show us the universe as an infant, and in some cases, as a newborn only a few 100 million years old. Nobody had a way to actually see that infancy directly until space telescopes became powerful enough to gather the almost unimaginably faint light that's been traveling toward us for over 13 billion years. That's where the Hubble Space Telescope comes in. Hubble launched in 1990, and for its first few years it was, frankly, a disappointment, hampered by a flaw in its main mirror that blurred its images. Once astronauts corrected that flaw in a servicing mission in 1993, Hubble became one of the most productive scientific instruments ever built. But even a telescope as powerful as Hubble needed a clever strategy to see all the way back to cosmic dawn, and that strategy is what produced the images that eventually caused all this trouble. The images are called the Hubble Deep Field Observations, and they're some of the most important pictures in the history of astronomy. The idea was almost stupidly simple. Point the telescope at a patch of sky that looks completely empty to the naked eye, smaller than a grain of sand held at arm's length, and just leave the shutter open for hundreds of hours, letting as much faint, ancient light build up as possible. The first Hubble Deep Field, taken in 1995, pointed at a seemingly blank patch of sky near the Big Dipper and revealed roughly 3,000 galaxies packed into that tiny sliver of space, galaxies of every size, shape, and age, stacked behind each other in every direction. Nobody expected that much. It was one of those moments in science where a single image completely rewrote what astronomers thought they understood about how crowded the universe actually is. Follow-up observations pushed the technique even further. The Hubble Ultra Deep Field, taken in 2003 and 2004, exposed for even longer and captured galaxies fainter and more distant than anything seen before. Later still, deep surveys combining Hubble with ground-based telescopes and eventually with the James Webb Space Telescope pushed the boundary back even further into an era astronomers now call cosmic dawn, the period within the first billion years after the Big Bang when the very first stars and galaxies were switching on. According to the standard model of cosmology, what we should see at that point is a mess. Small, primitive, irregular blobs of gas and stars, still in the process of colliding and merging their way up to something bigger. Building blocks, not finished products. That is not what Hubble found, and it's definitely not what James Webb found once it started peering even deeper. Instead, astronomers found galaxies that were already too large, too organized, and too mature to exist that early. Some contained hundreds of billions of stars. Some already had clean, well-defined spiral structure, the same kind of pinwheel shape our own galaxy has today. Some already had supermassive black holes sitting at their centers, actively feeding and glowing brightly enough to be detected across billions of light years. These are the hallmarks of a galaxy that has had billions of years to settle down and mature, but the universe hadn't been around that long yet. These galaxies looked like they'd been alive for eons in a universe that was still practically a newborn. To understand exactly why this is such a problem, you need to understand the model these observations are breaking. It's called lambda cold dark matter, or lambda CDM for short, and it is, without exaggeration, one of the most successful theories in the history of science. The name itself tells you what's inside it. Lambda refers to the cosmological constant, the term Einstein originally introduced and later regretted, which today is used to represent the mysterious dark energy that's accelerating the expansion of the universe. Cold dark matter refers to the invisible form of matter that makes up roughly 85% of all the matter in the universe. Matter that doesn't emit or absorb light, but still exerts gravity, cold meaning it moves slowly compared to the speed of light, which matters a great deal for how structure forms. This model explains an extraordinary range of observations. It explains the pattern of the cosmic microwave background, the leftover glow from 380,000 years after the Big Bang, first mapped in detail by the COBE satellite in the early 1990s, then with far greater precision by the WMAP satellite in the 2000s, and finally with exquisite precision by the European Space Agency's Planck satellite in the 2010s. It explains the large-scale web of galaxies we see spread across the universe today, the enormous filaments and voids that show up clearly in modern galaxy surveys. It explains the expansion history of the cosmos in exquisite detail, matching everything from the abundance of light elements formed minutes after the Big Bang to the rate at which galaxies are flying apart from each other today. Massive computer simulations, like the Millennium simulation and its successors, have used the lambda CDM model to simulate the entire evolutionary history of the universe from the smooth early state all the way to the present, and the resulting simulated universes look remarkably similar to what we actually observe around us. In this model, the universe started out in an extremely smooth, nearly uniform state. That cosmic microwave background shows matter distributed almost perfectly evenly, with only tiny ripples, differences of about 1 part in 100,000 between the densest and emptiest regions. Those ripples are thought to have originated from quantum fluctuations during an extremely brief period of exponential expansion called inflation, which happened in a fraction of a second after the Big Bang, and then got stretched up to cosmic scales as the universe expanded. Over time, gravity took those tiny ripples and turned them into everything we see today. Slightly denser regions pulled in a little more matter than their surroundings. That made them a little denser still, which let them pull in even more matter, and so on, in a slow, self-reinforcing process. Eventually, those regions collapsed into what are called dark matter halos, invisible scaffolding that ordinary matter then fell into, cooling and condensing to form the first stars and the first galaxies. This is a gradual process by nature, and that gradualness is baked into the physics itself. Gravity can only pull things together as fast as light can carry information about where the mass actually is located, so nothing about this collapse can happen instantly, no matter how strong the gravitational pull is. Small galaxies should form first, because they require less time and less material to come together. Bigger galaxies, the really massive ones, are supposed to be assembled later, built up gradually through repeated mergers of those smaller pieces, a process astronomers call hierarchical structure formation. Our own Milky Way is a perfect example of how this is supposed to work. Evidence from stellar populations and detailed simulations suggests the Milky Way grew through the merger and absorption of dozens of smaller galaxies over roughly 13 billion years, including a major collision with a smaller galaxy nicknamed Gaia Enceladus billions of years ago that left a permanent, still detectable signature in the orbits of stars in our galactic halo. That's how galaxy growth is supposed to look: slow, additive, built brick by brick over the entire history of the universe. So here's the actual contradiction, stated as plainly as possible. If large galaxies are supposed to be assembled gradually, over billions of years, through repeated mergers of smaller pieces, then finding a large, mature, well-organized galaxy in the first few 100 million years of the universe simply doesn't fit inside that framework. There hasn't been enough time for the mergers to happen. There hasn't been enough time for the structure to settle into spiral arms. There hasn't been enough time to grow a supermassive black hole through the normal, gradual process of feeding on surrounding gas. And yet, there they are, fully formed, in a universe barely out of its infancy, sitting in Hubble's and Webb's images like something that simply shouldn't have had time to happen yet. Let's go through the specific categories of what was actually found, because too big, too early undersells just how strange some of these objects are, and it helps to put names and numbers to them. The first category is massive galaxies at extreme redshift. Redshift is simply how astronomers measure both distance and time in the universe. As the universe expands, light traveling toward us gets stretched out along the way, shifted toward longer, redder wavelengths, the same way an ambulance siren drops in pitch as it moves away from you. The more the light has been stretched, the further it has traveled, and the further back in time we're seeing, because that light left its source a very long time ago and has been journeying toward us ever since. Astronomers found galaxies at redshifts of 9, 10, 11, and beyond, corresponding to a universe less than 500 million years old. One of the most famous early examples, a galaxy called GNZ11, was confirmed at a redshift of just over 11, corresponding to roughly 400 million years after the Big Bang, and it turned out to be surprisingly bright and surprisingly massive for something that far back. Some of these early galaxies already contain hundreds of billions of solar masses worth of stars, on par with the Milky Way today, a galaxy that took the entire history of the universe to build up to its current size. There simply isn't a version of the standard model where hierarchical, merger-driven growth produces something that massive that quickly. It would be like finding a fully built skyscraper in a city that broke ground yesterday. The second category is mature structure at impossibly early times. Some of these early galaxies already show clear spiral arms, the kind of organized, rotating disk structure that normally takes billions of years to settle into place. A spiral galaxy isn't just a random pile of stars scattered together, it's a flattened, rotating disk that has cooled down, settled into a stable configuration, and developed density waves, regions of compression that move through the disk and trigger new star formation, which is what creates those characteristic spiral arms in the first place. That's a slow, gradual process that depends on the disk having enough time to settle and stabilize without being disrupted by mergers or violent interactions. Finding it in a galaxy less than 1 billion years old is like finding a fully grown oak tree, complete with rings marking decades of seasonal growth, in a forest that was planted last spring. The third category is supermassive black holes that shouldn't have had time to grow. Most large galaxies, including our own, have an enormous black hole sitting at their center. The Milky Way's is called Sagittarius A star, and it weighs in at about 4 million times the mass of the Sun, which sounds huge until you compare it to some of the monsters found at the centers of other galaxies, some of which weigh in at 10 billion solar masses or more. Some of the earliest galaxies observed appear to host black holes with masses in the range of hundreds of millions to billions of solar masses. Black holes grow by pulling in surrounding matter, a process called accretion, but there's a hard physical limit to how fast it can happen, called the Eddington limit, named after the astrophysicist Arthur Eddington. Feed a black hole too fast, and the sheer intensity of the radiation produced by all that infalling matter actually pushes new material away before it can fall in, capping the growth rate no matter how much fuel is available nearby. Even if you assume one of these early black holes has been growing at the absolute maximum possible rate, continuously, without interruption, since the first instant after the Big Bang, the numbers barely work for some of them, and for the most extreme cases, they don't work at all, even with the most generous assumptions plugged in. So the question becomes genuinely uncomfortable for cosmologists. Where did these black holes come from? And how did they get so big so fast, when the physics of accretion says they shouldn't have had time? The fourth category is chemically mature galaxies. In astronomy, anything heavier than hydrogen and helium is called a metal, even elements like carbon, oxygen, nitrogen, and iron, which is a strange use of the word compared to everyday language, but it's the standard terminology across the field. Metals don't exist at the very beginning of the universe. The Big Bang produced almost nothing but hydrogen and a bit of helium, with trace amounts of lithium. Every heavier element in existence, including the calcium in your bones, the oxygen you're breathing, and the iron in your blood, was forged inside a star and scattered into space when that star died, usually in a supernova explosion or through a slower process of stellar winds. That enriched material then mixes into surrounding gas clouds over time, which is where the next generation of stars forms, now carrying a bit more of those heavier elements than the generation before it. This is a slow, multi-generational process by necessity, because it requires stars to be born, live out their lives, and die, sometimes over millions or billions of years depending on their mass, before their contribution to the surrounding chemistry even becomes available. But early galaxies have been found that already show significant metal content, meaning multiple generations of stars had already lived and died in an era when there should barely have been time for even one full generation to run its course from birth to death. Every one of these findings on its own would be an interesting anomaly, worth a paper and a conference talk. All four of them showing up together, in the same handful of early galaxies, is what turns this from an interesting curiosity into something the entire field of cosmology has had to take seriously, and it's part of why some astronomers have started informally referring to the most extreme examples as universe breakers, a nickname that's only half joking. So what are the possible explanations? Scientists have laid out a handful of them, and it's worth going through each one honestly, including where it falls short, because none of them are a clean, fully satisfying fix on their own, and that's precisely what makes this such an active and genuinely unresolved area of research rather than a solved problem waiting for someone to write it up. The first possibility is the least exciting, but it's also the most responsible place to start. The observations themselves might be wrong, or at least overstated. Maybe the distances have been overestimated. Maybe the masses have been overestimated. This is always worth checking first in science, because extraordinary claims deserve extraordinary scrutiny, and astronomy has a long history of early, dramatic results getting walked back once more careful follow-up data comes in. There is some real truth to this option here. Several of the most extreme early claims about impossible galaxies have had their estimated masses revised downward once follow-up spectroscopic observations came in, because the primary method used to estimate a galaxy's distance and age from its color alone, called photometric redshift, carries real, quantifiable uncertainty, especially at these extreme distances where the light is faint and the available data is limited. Spectroscopy, which spreads a galaxy's light out into a detailed rainbow and looks for specific absorption or emission lines from known elements, gives a much more precise redshift measurement, but it requires more observing time and isn't available for every candidate. But here's the thing, even after accounting for that uncertainty, even after multiple independent research teams using different techniques and different instruments double-check the results, the core problem doesn't go away. These galaxies are real, their distances are well established through spectroscopic confirmation in many of the most important cases, and their masses, even at the conservative low end of the error bars, are still bigger than the standard model comfortably allows for at these early times. The second possibility is that star formation in the early universe was simply more efficient than we've assumed based on studying nearby, present-day galaxies. If gas converted into stars faster and more completely back then, galaxies could pack on stellar mass much more quickly than our current models predict, without needing any exotic new physics at all. There's actually a reasonable physical argument for why this might be true. The very first generation of stars, sometimes called population 3 stars, formed from pure hydrogen and helium with none of the heavier elements that exist in gas clouds today, because those heavier elements simply hadn't been produced yet. Without those heavier elements, which normally help gas clouds cool down efficiently and fragment into many smaller stars, the first stars may have formed differently, potentially growing much larger and more massive on average than typical stars today, and possibly forming more efficiently as well. But there's a limit to how far you can push this idea. If too much gas turns into stars too quickly, the resulting radiation, stellar winds, and supernova explosions from all those young, massive stars should blow the remaining gas out of the galaxy entirely, and shut down further star formation almost as quickly as it started. You can't just crank up the efficiency dial indefinitely without running into that self-limiting feedback. So this explanation has to thread a fairly narrow needle to work. The third possibility is that our model of dark matter itself is incomplete or wrong in some important way. Dark matter is the invisible scaffolding the galaxies form around, and in the standard model it's assumed to be cold, meaning it moves slowly compared to light, and collisionless, meaning individual dark matter particles only interact with anything else, including each other, through gravity. If dark matter actually behaves differently than that simple picture, if it's warmer and moves faster, or interacts with itself through some additional force, or responds to a hidden dark sector we haven't identified yet, the entire timeline of when and how cosmic structure forms could shift in ways that might allow for faster galaxy assembly. The problem is that these alternative dark matter models, things like warm dark matter or self-interacting dark matter, have already been studied in a lot of depth over the past couple of decades, and most of them actually make the early galaxy problem worse rather than better, because they tend to suppress the growth of small-scale structure rather than accelerate it, which is the opposite of what would be needed here. The fourth possibility is the most dramatic, and the one that gets the most attention in headlines. There's new physics we simply haven't discovered yet. Maybe the early universe behaved in ways that our current theories, general relativity, and the standard model of particle physics simply don't capture, because those theories have never actually been tested under the extreme densities and energies of the first moments after the Big Bang. This isn't a cop-out, and it isn't unprecedented. Physics has changed direction before when observations stubbornly refused to match theory, most famously when the unexpected orbit of Mercury eventually helped confirm that Newtonian gravity needed to be replaced by Einstein's general relativity. But it is the option that requires the most caution among cosmologists, because new physics is also the easiest explanation to reach for when you don't have a better one on hand, and a responsible version of this proposal needs to be backed by a specific, testable prediction, not just invoked vaguely as a placeholder for our ignorance. Then the James Webb Space Telescope came online in earnest at the start of 2022, following its Christmas Day launch in 2021, and a nail-biting month-long journey out to its observing position nearly 1 million miles from Earth, at a gravitationally stable point called the second Lagrange point, or L2. And instead of resolving the tension that Hubble had already uncovered, Webb made it substantially worse. Webb's instruments, particularly its near-infrared camera, are specifically designed to see further into the infrared than Hubble ever could, which matters enormously here, because light from the most distant galaxies has been stretched so much by cosmic expansion that it's shifted almost entirely out of visible light and deep into the infrared by the time it reaches us. That capability lets Webb catch light from galaxies even earlier in cosmic history than Hubble could ever hope to reach. Dedicated Webb survey programs with names like CERS, JADES, and GLASS were specifically designed to hunt for these extremely early galaxies, and they delivered results almost immediately after the telescope started operating, results that surprised even scientists who had been expecting some tension with the standard model going in. Webb has found galaxies at redshifts of 13, 14, and possibly beyond, corresponding to a universe only around 300 million years old, pushing the observational frontier back by roughly 100 million years compared to what Hubble alone had managed. Some of these are already surprisingly massive. One in particular, catalogued as JADES GSZ 13-0, was confirmed at a redshift of roughly 13.2, corresponding to a galaxy we're seeing as it looked about 320 million years after the Big Bang. That galaxy already contains something on the order of 1 billion solar masses and stars, built in a window of time that, by the standard model's own math, shouldn't have allowed for anywhere near that much stellar mass to accumulate. Other candidates, some still awaiting full spectroscopic confirmation, have been reported at even higher redshifts, and a handful of extremely bright, extremely massive candidates from the earliest Webb surveys were specifically flagged by researchers as the kind of universe-breaking objects that would be genuinely difficult to explain within the standard framework if their extreme properties held up under further scrutiny. Webb has also picked up clear signs of actively feeding supermassive black holes at these extreme early times, black holes that appear to have formed almost immediately after the Big Bang, cosmically speaking, with masses that strain our understanding of how black holes are seeded in the first place and how fast they're physically able to grow afterward. In several cases, Webb has detected the specific spectral signatures of gas being violently accelerated by a black hole's gravity, direct evidence of active feeding rather than just an inferred mass estimate from indirect clues. And it's not just isolated extreme cases scattered here and there. Webb shows that the early universe, as a whole, was more varied and more active than the standard model expected, with a genuine mix of galaxy types, morphologies, and evidence of ongoing star formation and chemical enrichment happening far sooner than the traditional, simplified version of cosmic history had allowed for. The picture that's emerging from several years of Webb observations now is of a universe that grew up faster than nearly anyone predicted before the telescope launched, and right now, nobody in the field has a single, complete, broadly accepted explanation for why. With all of that in mind, here are the leading proposals currently being discussed for what might actually be going on, brought together into one unified list instead of scattered across separate conversations, because in practice, these ideas are being tested and debated together rather than in isolation. The first is enhanced star formation efficiency, the idea that gas converted into stars faster and more completely in the early universe than it does in galaxies today. Some recent work has specifically proposed that early galaxies may have gone through short, extremely intense bursts of star formation, sometimes called bursty star formation, rather than forming stars at a steady, gradual rate the way most present-day galaxies do. A short, incredibly intense burst could make a young galaxy appear far more massive and far brighter than its underlying, more modest total mass would suggest, at least temporarily. The catch, as mentioned earlier, is that pushing star formation efficiency too far should trigger enough radiation pressure and explosive supernova feedback to blow the remaining gas out of the galaxy before it can grow this large and disorganized. So there's a narrow window where this idea could genuinely work, and it remains an open question whether the observed galaxies fit neatly inside that window or push beyond it. The second is primordial black hole seeding. Instead of black holes starting out small, as the collapsed remnants of massive dying stars, and then slowly growing over billions of years through gradual accretion, what if some black holes formed directly in the extremely early universe, before any stars existed at all, as a direct result of unusually dense regions of the primordial universe collapsing under their own gravity almost instantly? A black hole that starts out already at a few thousand or even a few million solar masses gets an enormous head start compared to one that has to begin from the remnant of a single dying star, and could plausibly reach hundreds of millions or billions of solar masses by the time we're observing it, without needing to violate the Eddington limit nearly as dramatically. The catch is that this requires very specific, currently unconfirmed conditions in the first fraction of a second after the Big Bang, the kind of exotic, high-energy physics that's entirely plausible in theoretical models, but hasn't yet been directly confirmed through observation, leaving it as an intriguing but unproven possibility. The third is modified dark matter behavior. If dark matter isn't simply cold and collisionless the way the standard model assumes, if it interacts with itself through some additional force, or exchanges energy with an unseen dark radiation component, or responds to physics beyond simple gravity, the entire timeline of how dark matter halos collapse and how galaxies subsequently form within them could shift in ways that allow for faster assembly. The catch, again, is that most of the alternative dark matter models that have already been proposed and tested against other independent observations over the past 2 decades tend to suppress small-scale structure formation rather than accelerate it, which cuts directly against what would actually be needed to explain unusually fast, unusually massive early galaxies. The fourth is feedback working in reverse of its usual role. Under normal circumstances, the radiation and explosive energy produced by young stars and actively feeding black holes pushes surrounding gas away and slows down further star formation, acting as a natural brake on galaxy growth. That's a stabilizing, self-limiting process that keeps galaxies from growing too fast too quickly under most conditions. But under certain extreme conditions, particularly at the very high densities present in the earliest galaxies, that same energy might actually compress surrounding gas instead of dispersing it outward, triggering a runaway burst of additional star formation rather than shutting the process down. The catch is that positive feedback loops of this kind tend to run away entirely once they get started, which raises an uncomfortable follow-up question. If this mechanism is real and effective, why don't we see even more extreme, even more massive early galaxies than the ones actually observed, rather than a comparatively modest handful of unusually large examples? The fifth is that some of the most extreme individual claims are, at least in part, measurement artifacts rather than genuine physical anomalies. As mentioned earlier, several of the most dramatic early results reported in the first year or two after Webb began operating have had their mass estimates revised downward, as more detailed follow-up spectroscopic data came in, because the redshift measurement technique typically used at these extreme distances carries real, quantifiable uncertainty that's easy to underestimate in a first, quick analysis. This possibility doesn't erase the underlying problem entirely, since even the most conservative, carefully revised estimates for the best confirmed cases are still in meaningful tension with the standard timeline for hierarchical galaxy assembly, but it's an important and honest part of the full picture, and it's worth remembering that not every dramatic headline about an impossible galaxy has held up perfectly under closer, more careful scrutiny over time. None of these 5 ideas fully solves the problem entirely on its own. Each one comes with real limitations, each one creates new questions even as it partially answers old ones, and that combination is exactly why this remains an open, actively debated problem at the center of modern astrophysics rather than something that's already been quietly settled behind the scenes. It's worth stepping back at this point and asking why any of this actually matters beyond the specialized world of professional astronomers publishing papers in journals most people will never read. First, it's a genuine stress test for our most fundamental physical theories. General relativity and the standard model of particle physics are the 2 central pillars holding up essentially all of modern physics, and they've been tested with extraordinary, almost unbelievable precision here on Earth, inside particle accelerators like the Large Hadron Collider and through instruments like the LIGO and Virgo gravitational wave detectors. But neither theory has ever really been tested under the truly extreme conditions that existed during the first few 100 million years after the Big Bang, when densities and energies were far beyond anything we can currently recreate in a laboratory. If explaining these early galaxies genuinely requires new physics of some kind, then new physics almost certainly wouldn't stay neatly confined to some obscure, irrelevant corner of cosmology. It could ripple outward and reshape how physicists understand the fundamental behavior of matter and energy more broadly, with consequences reaching well beyond astronomy. Second, this entire question touches directly on the story of cosmic history itself, the grand narrative that connects the Big Bang all the way through to the formation of stars, planets, and eventually life, including our own. If the earliest chapters of that story genuinely need a serious rewrite, it changes how astronomers think about everything that came afterward in the sequence, potentially including questions like how common or rare it actually is for a universe to produce the right conditions for something like life to eventually emerge, and for beings capable of building space telescopes to eventually look back and ask these very questions. Third, and maybe the most philosophically interesting angle of all, this raises a deeper question about how genuinely predictable the universe actually is at a fundamental level. Science as a discipline runs on the ability to make a specific prediction ahead of time, and then rigorously test that prediction against real observations afterward. The standard cosmological model made a fairly specific, quantitative prediction about how quickly galaxies of a given mass could plausibly form after the Big Bang, and the accumulating observational evidence from both Hubble and Webb is pushing back hard against that particular prediction, even as the model continues to succeed brilliantly in almost every other domain it's been tested against. That tension could simply mean the model needs a targeted update in this one specific area, which would be a completely normal, healthy part of how science typically progresses over time. Or, more unsettlingly, it could mean that the very early universe involved a degree of randomness or an unusual sensitivity to specific initial conditions that current models simply don't capture, in which case our overall confidence in extrapolating comfortably from well-tested, nearby physics into completely unknown, extremely early conditions might need to come down a notch across the board, not just in this one narrow area. Looking ahead, this isn't a mystery that's likely to stay unresolved forever. Several upcoming and currently planned instruments are specifically expected to help settle at least parts of this debate over the coming decade. The Nancy Grace Roman Space Telescope, expected to launch in the second half of the 2020s, is designed with an extremely wide field of view compared to Webb, which means it will be able to survey much larger patches of sky and discover far more of these extremely distant, extremely early galaxy candidates for Webb and other observatories, to then study in much greater individual detail afterward. On the ground, next-generation giant telescopes currently under construction, including the extremely large telescope in Chile, will bring far larger mirrors and correspondingly sharper resulting power to bear on these same extremely faint, extremely distant targets, potentially allowing for even more precise mass and structure measurements than are currently possible. And Webb itself is still relatively early in its planned operational lifetime, which means the sample of confirmed, spectroscopically verified early galaxies is only going to keep growing larger and more statistically robust over the next several years, giving theorists an increasingly solid observational foundation to actually test their competing proposed explanations against, rather than working from the smaller, more uncertain sample of candidates available today. Before we get to where this leaves us, it's worth addressing something that comes up constantly in discussions of a topic like this, because it's a fair and reasonable question. Does this mean the Big Bang is wrong? Does this mean the whole standard model of cosmology is about to collapse? The honest answer is almost certainly not, and it's worth explaining why, because understanding that distinction actually makes the real mystery more interesting, not less. The Big Bang model itself rests on several independent pillars of evidence that have nothing to do with early galaxy formation. The expansion of the universe, first measured by Edwin Hubble in the 1920s and confirmed with vastly greater precision ever since, is one pillar. The cosmic microwave background radiation, the actual leftover heat from the early universe, matching theoretical predictions with breathtaking accuracy across the entire sky, is another. The observed abundance of light elements like hydrogen, helium, and lithium, produced in the first few minutes after the Big Bang in a process called primordial nucleosynthesis, matching what the theory predicts almost exactly, is a third. None of these pillars are threatened by the early galaxy problem. What's actually being challenged is a much more specific, narrower piece of the model, the detailed timeline of exactly how quickly gas collapses into stars, and how quickly those stars assemble into galaxies once the basic Big Bang framework is already up and running. That's a meaningful problem, and it might eventually require real modifications to part of the model, but it's the difference between renovating a room in a house and discovering the house has no foundation. It's useful to keep that distinction in mind, because sensational headlines sometimes blur the line between "there's an unresolved tension in one part of a hugely successful theory," and "the entire theory has collapsed." And those are very different claims with very different levels of evidence behind them. It also helps to put this in historical context, because this isn't actually the first time cosmology has faced a genuine crisis that forced real changes to the standard picture. In the late 1990s, two independent teams of astronomers, studying exploding stars called Type Ia supernovae as distance markers, discovered that the expansion of the universe wasn't slowing down under its own gravity the way everyone expected. it was speeding up. That discovery was so unexpected that many astronomers assumed there had to be some kind of measurement error or overlooked systematic effect. Instead, it turned out to be real, and it led directly to the modern understanding of dark energy, the mysterious lambda and lambda CDM, now understood to make up roughly 70% of the total energy content of the universe. Nobody predicted dark energy in advance. The universe forced it on cosmologists through a stubborn observational anomaly that refused to go away, no matter how carefully it was checked, very similar in spirit to what's happening with these early galaxies right now. More recently, there's an ongoing, separate puzzle called the Hubble tension, where different methods of measuring exactly how fast the universe is expanding today keep giving answers that disagree with each other by more than their stated margins of error should allow, no matter how carefully each individual measurement is checked and rechecked. Nobody has fully resolved the Hubble tension yet either, and some cosmologists suspect that this early galaxy puzzle and the Hubble tension might eventually turn out to be connected, both symptoms of some deeper, currently unidentified issue with part of the standard model, though that connection remains speculative rather than an established fact at this point. This pattern is actually a healthy, normal part of how science works, even though it can feel unsettling from the outside when you're used to a simplified textbook version of a theory presented as a finished, settled product rather than the constantly tested, occasionally revised, living framework it actually is in practice. A good scientific theory isn't one that's never challenged by new data. It's one that makes specific, falsifiable predictions, gets tested rigorously against real observations, and then either survives that testing, gets refined at the edges to accommodate new findings, or in rarer cases gets replaced entirely by something that explains everything the old theory explained plus the new anomaly as well. Lambda CDM has survived an enormous number of tests over the past several decades, which is exactly why cosmologists don't casually throw it out the moment a new puzzle shows up. But a theory that had never once been challenged by any new piece of data in over 20 years would actually be somewhat suspicious in its own right, less because it's too successful and more because it would suggest nobody had pushed it hard enough yet with sufficiently precise new instruments. Powerful new telescopes, like Webb, are precisely the kind of instrument capable of applying that kind of pressure, and finding a genuine crack somewhere is, in a strange way, a sign that the underlying scientific process is working exactly as intended. It's also worth briefly touching on some of the more fringe, or alternative explanations that occasionally circulate around this topic, partly because a responsible treatment of this subject should address them, and partly because understanding why most working cosmologists don't take them seriously helps clarify what a genuinely strong alternative theory would actually need to look like. Some commentators have suggested this could be evidence for entirely different cosmological models, alternatives to the standard Big Bang framework itself, sometimes invoking ideas like tired light, an old and thoroughly discredited proposal from decades ago suggesting that light simply loses energy as it travels vast distances rather than the universe actually expanding. The problem with tired light and similar alternative proposals is that they were tested rigorously against multiple independent lines of evidence long ago, including extremely precise measurements of how the light from distant supernovae is stretched out in time as well as in wavelength, something tired light cannot explain, but standard cosmic expansion explains naturally and precisely. These alternative frameworks don't just fail to explain the early galaxy problem better than the standard model, they actively fail to explain a whole range of other, completely unrelated observations that the standard model handles easily, which is exactly why they remain fringe positions rather than serious contenders discussed in mainstream astrophysics journals. The real, live scientific debate isn't happening between the Big Bang and some rival cosmological framework, it's happening entirely within the Big Bang picture, over the specific details of how fast structure is able to form within it. Let's also spend a moment on what actually resolving this problem would look like in practice, because it's not going to be a single dramatic press conference announcing an answer. It's going to be a gradual accumulation of better data across several different fronts simultaneously. Spectroscopic confirmation is one major front. Right now, plenty of the most extreme, most talked about early galaxy candidates only have redshift estimates based on their color, the photometric method mentioned earlier, which carries meaningful uncertainty. Getting a full spectrum for each of these candidates, spreading their light out, and confirming their exact distance using known atomic emission or absorption lines is slower and more resource-intensive, but it's also far more reliable, and it's the single biggest thing that would separate the genuinely extreme, confirmed cases from candidates that might turn out to be closer, less massive, or otherwise more mundane once properly checked. Mass estimation is a second major front. Even for galaxies with a confirmed distance, estimating their total stellar mass involves a chain of assumptions about how starlight relates to underlying mass, assumptions that were mostly built by studying nearby, present-day galaxies, and that might not transfer cleanly to a very different, much younger cosmic environment. Refining those assumptions, ideally using multiple independent methods that can be cross-checked against each other, would tighten the mass estimates considerably and either sharpen or soften the tension with the standard model depending on which way the numbers move. A third front is simply expanding the overall sample size. Right now, the most extreme, universe-breaking, candidates number in the dozens rather than the hundreds, which means individual unusual objects can carry outsized influence on the overall conclusion. A much larger, statistically robust sample, the kind that wide-field surveys from Roman and other future instruments are specifically designed to build, would let researchers ask a more powerful, more reliable question. Not just, does this one exceptional galaxy break the model, but what fraction of galaxies at this early era are actually this massive, and does that fraction genuinely exceed what the model predicts across a large, representative population, rather than just in a handful of cherry-picked, extreme individual cases? There's also a quieter but genuinely important angle to all of this worth mentioning, which is what it says about the culture and self-correcting nature of science more broadly, something that's easy to lose sight of amid the more dramatic headlines. When the very first extreme early galaxy candidates from Webb were announced, they generated enormous public excitement and a wave of headlines proclaiming that cosmology was broken. Since then, the community has done exactly what a healthy scientific process should do. Some of the most extreme individual claims have been walked back or revised downward with better data, exactly as responsible caution would predict. Other claims have held up and even strengthened under additional scrutiny, becoming more solidly confirmed rather than less. Competing theoretical explanations have been proposed, tested against the data, and in some cases already ruled out or significantly constrained by follow-up observations, narrowing the field of viable explanations over time even without landing on one single final answer yet. That messy, iterative, occasionally contradictory process, watched from the outside in something close to real time, is what genuine science in progress actually looks like, and it's very different from the neat, tidy, already settled version of scientific knowledge most of us grew up learning in school textbooks, where a chapter presents a theory as an established, uncontested fact without much sense of the sometimes decades-long, frequently uncertain process that produced it. There's one more layer worth digging into before we wrap up, because it connects this story to some of the biggest open questions in physics as a whole, questions that extend well beyond just galaxies and telescopes. If it does turn out that some form of genuinely new physics is required to explain how these galaxies grew so large so quickly, where in the chain of cosmic history would that new physics actually need to sit? One candidate is inflation itself, that extremely brief period of exponential expansion in the first fraction of a second after the Big Bang that's thought to have stretched tiny quantum fluctuations up into the seeds of all future cosmic structure. The simplest inflationary models predict fluctuations that are nearly identical in strength across every scale, which is exactly what's been measured in the cosmic microwave background with remarkable precision. But nearly identical isn't the same as perfectly identical, and some theorists have proposed that inflation might have produced slightly enhanced fluctuations on the particular scales that would go on to become galaxies, without violating anything currently measured in the cosmic microwave background. Because the galaxy-forming scales are smaller and harder to probe directly with current cosmic microwave background data than the very large scales that have been measured so precisely. If that turns out to be correct, it wouldn't require throwing out inflation as a concept. It would mean refining exactly which version of inflation matches reality out of a large family of similar, but not identical theoretical models that have been proposed by physicists over the past several decades. Another candidate sits even earlier, in the physics of the very first moments after the Big Bang, before inflation even finished, when energies were far beyond anything that's ever been recreated in a particle accelerator on Earth. Some proposals suggest that exotic physics at these energies, potentially connected to grand unified theories that attempt to merge the fundamental forces of nature into a single unified framework, could have left subtle imprints on how matter was distributed in the earliest universe. Imprints that wouldn't necessarily show up clearly in the cosmic microwave background, but could still influence how quickly the first galaxies were able to form. This is speculative territory, admittedly, but it's the kind of speculation that's directly motivated by a real, measured anomaly rather than pure guesswork, which is an important distinction in how seriously the physics community tends to take an idea. A proposal invented specifically to explain an actual, confirmed observational puzzle carries more weight than a proposal invented purely for its own theoretical elegance with no supporting data behind it. It's also worth touching briefly on how this connects to the search for life elsewhere in the universe, even though that connection is more indirect than some of the other threads we've covered. The timeline of when the first galaxies, and therefore the first stars, and therefore the first opportunities for heavy elements and eventually planets to form, matters quite a bit for questions about how early in cosmic history life could have first become possible anywhere in the universe. If galaxies and the heavy elements needed for rocky planets showed up earlier than previously thought, in principle that opens the door slightly wider for the earliest possible moment when life-supporting conditions could have existed somewhere in the cosmos, even if our own solar system didn't form until roughly 9 billion years after the Big Bang. This doesn't tell us anything directly about whether life actually did emerge earlier elsewhere. That's a completely separate and much harder question, but it does adjust the boundaries of what's theoretically possible, and cosmologists studying the early universe and astrobiologists studying the conditions for life increasingly find their work overlapping at this particular edge of the field. Bringing this back down to something more concrete, it's worth remembering just how young this specific chapter of the story actually is. Webb has been fully operational for only a few years at this point, and every single one of the extreme early galaxy candidates discussed here was discovered within that short window. Compare that to how long it took astronomers to fully nail down and resolve earlier cosmological puzzles. The accelerating expansion of the universe took the better part of 2 decades to go from an unexpected result to a fully accepted, Nobel Prize-winning piece of the Standard Model, complete with a specific physical explanation, dark energy. That's now built into essentially every modern cosmological calculation. If the early galaxy problem follows a similar timeline, we may well be sitting right near the very beginning of a story that won't be fully resolved for another decade or two, which means anyone paying attention right now is essentially watching the opening chapters of what could eventually become one of the more significant developments in modern physics, in something close to real time, rather than reading about it afterward as settled history in a textbook. So where does all of this actually leave us right now, at this particular moment in the ongoing story? We have a universe that, according to its own baby pictures preserved in the cosmic microwave background, started out about as smooth and structurally simple as it's physically possible for a universe to be. And yet, within its first few 100 million years, a cosmic idling compared to its current age of nearly 14 billion years, it had already managed to produce galaxies with hundreds of billions of stars, cleanly organized spiral structure, and central black holes weighing in at billions of solar masses. A maternity ward with a fully grown adult standing calmly in the middle of it, and nobody working the front desk can fully explain how they got there. Whether the eventual, settled answer turns out to be genuinely new physics, a meaningful correction to how astronomers are currently measuring and interpreting these extremely distant objects, or some previously overlooked detail about how the very first generation of stars and black holes actually formed and grew, this remains one of the most genuinely open, most actively contested questions anywhere in modern astronomy, and it's playing out in something close to real time, one new Webb observation, one new follow-up spectrum, one new theoretical paper at a time. Every few months brings another candidate galaxy pushing the redshift record a little further back, another round of careful follow-up measurements tightening or loosening the tension with the standard model, another small piece of evidence pulling the overall picture a little more one way or the other. Right now, at this exact moment, nobody has the final, complete answer. And honestly, that ongoing uncertainty, that sense of a genuine scientific mystery still actively unfolding rather than something safely finished and filed away in a textbook, is exactly what makes this such a compelling story to follow. It's worth sitting with the scale of what's actually being discussed here for a moment longer, because it's easy to let phrases like hundreds of millions of years and billions of solar masses wash past without really registering what they mean. 300 million years, the age of the universe, when some of the most extreme Webb candidates existed, is shorter than the time it takes a single star like the Sun to complete 1.5 orbits around the center of the Milky Way. It's a blink, cosmically speaking, and yet inside that blink, according to the observations, nature managed to assemble structures containing more mass in stars than exists in our entire galaxy today, a galaxy that had the full 13.8 billion year age of the universe available to build itself up gradually, piece by piece. That comparison is really the heart of why this problem has captured so much attention, both inside the scientific community and outside it. It isn't a subtle statistical discrepancy buried in a footnote, it's a direct, visceral mismatch between how long something is supposed to take and how quickly it apparently happened anyway, the kind of contradiction that's easy to explain to a general audience precisely because it doesn't require advanced physics to feel wrong, only a basic sense of how long things normally take to grow. That combination, a problem serious enough to genuinely worry professional cosmologists, but simple enough in its core logic to explain clearly to anyone willing to spend an hour thinking about it, is fairly rare in modern physics, where a lot of the most interesting open questions are locked behind years of specialized mathematical training before they even make sense. This one doesn't require that. Anyone can grasp the basic shape of the problem. Gravity takes time to build big things. We know roughly how much time was available, and what we're seeing appears to be bigger than that amount of time should allow. Everything after that initial realization, the specific proposed solutions, the details of dark matter models, the mechanics of black hole accretion, is really just an extended exploration of that one simple, sturdy idea, examined from as many angles as the current data allows. That's ultimately why this deserves more than a single quick headline and a shrug. It sits at a genuinely rare intersection, an open question that active researchers are still fighting over in real published papers, that new data from an operating space telescope is actively reshaping practically every year, and that doesn't require a physics degree to appreciate why it matters. Whatever the eventual answer turns out to be, whether it's a modest correction to some of our current assumptions about early star formation, or something considerably stranger involving physics we haven't fully worked out yet, the fact that the universe is still capable of surprising the people who study it this profoundly, more than a century after Einstein, and nearly 7 decades after the Big Bang model first took shape, says something worth remembering. Even our best, most successful theories are still just our best current attempt at describing something vastly larger and older than the tools we're using to study it, and every so often, the universe reminds us of exactly that.